What was I going to say? I was just going to say something, but I forgot. Anyway, yeah. So, like I wrote in the Blackboard post, I'm just going to assume that you're good. If you need help with that, like on doing the product rule stuff, make sure you get help. Okay, find Cerny, find me, get the help that you need if there were problems you got stuck on. Okay. Okay. So next type of rate of change function that we're going to work on antiderivatives is what's called a rational function. A rational function, it has the word ratio in it. And so what is it? It's the ratio of polynomials. Ratio of polynomials. And we know polynomials are things like 5x cubed minus 4x squared plus 3. Those kinds of things, right? So when you put a ratio of those two, you get what's called a rational function. And certain types of rational functions can be, you can find the antiderivative by the technique we're going to do today, which is called partial fractions. Okay? But before we get to partial fractions, there's something that you want to do a check of. If you have a rational function like this one, 2x squared over x plus 1, that's a ratio of polynomials. And if you're, the first thing you want to check is check the degree. If the degree of the numerator is greater than or equal to the degree of the denominator, then you're going to begin by long division. You're not going to jump right into this partial fractions technique, which we'll talk about later, but the first thing you want to do is long division. Okay? And so long division of polynomials is the same thing, it's the same technique as long division of just values. You follow the same rules. So the first thing we want to do is you want to write a spot for every power of x, even if there's some are missing. So we can do 0x plus 0. But leave a space for every power of x. And if there's one missing, you just do 0 times that power of x. Okay, and then we're trying to figure out what things multiplied up here times the divisor, that's going to get us to equal that. So in other words, what times x gives us 2x squared? 2x. And we're going to put that above the x. That's going to go in the x column. So we're going to start with 2x. Why do we do that? Because when we multiply down, we get 2x squared plus 2x. And then when we subtract, y'all remember long division? We're going to subtract now. When we subtract, these go away. And that's what we wanted. That's why we picked 2x, so that this leftmost column is going to end up being 0. That's how long division works. So then we got 0x minus 2x, which equals negative 2x. Stop me if I lose you. Okay, stop me if I lose you. So now we're going to ask the question again. What times x equals minus 2x? Negative 2, and that's a constant, so that's going to go up here in the constant column. So we're going to do negative 2. So negative 2 times x plus 1 is going to be, oops. Oh, sorry, we got to bring down the 0. I forgot. Sorry, got to bring down the 0, right? And so then minus 2x minus 2. And then we're going to subtract, and when we subtract, we get our 0, right? So we're going to subtract this. And so when we subtract, we get plus 2. Stop me if I lose you. So what's that? That's the remainder. Which means we can rewrite 2x squared over x plus 1 as the quotient plus the remainder over the divisor. Remember that? So now this gives us a way to rewrite this integral as what? 2x minus 2 plus the remainder over the divisor. So those are equivalent. And now we got an easy one, right? So we've got our rate of change function in a different form, and we can do an easy antiderivative. Antiderivative is squared, antiderivative minus 2x, and then how do we do 2 over x plus 1? Hopefully that's easy by now too. Yes sir or no?
2 times the natural log of the absolute value.
Nailed it? Right, so this is like a really, really easy chain rule problem. It's x plus 1 to the minus 1. So it's going to be natural log. Don't forget the absolute value. It's a domain issue, right? So this has all x values are valid except -1. So we need our antiderivative to have the same domain. So we need that absolute value, and then we're going to need the plus c to get all antiderivatives, or all accumulation functions, starting from any value of a. So in this one, long division just did the trick. We didn't have to do anything else. Long division just gave us a form that we could just write down the answer. But sometimes this resulting fraction will need this technique called partial fractions, which we'll spend the rest of the day on. Okay. So long division might just outright give you a rate of change, a form of the rate of change function that you can find the antiderivative of easily, or you may be left with another problem here, which we would use partial fractions for. Partial fractions is what we're going to do the rest of the class. Okay. Questions on the long division or the antiderivative? Good on that one? Okay, so I should have started by saying that the most important technique of all these techniques that we spend these 2 weeks on is undoing the chain rule, the one we did the first. Why? Because it shows up the most often, and then as we learn all the new techniques, it comes into those. It'll find a role in these other techniques that we learn. Okay? So always ask, is it undoing the chain rule first, right? It's got to fit that form. So that's what we should have done first. We should have come up to this one and we should have said, is it undoing the chain rule? Is it undoing the chain rule? We could maybe rewrite it as 2x squared times x plus 1 to the minus 1. And we get 2x squared, x plus 1 to the minus 1. Is it undoing the chain rule? No, okay? Can you make one small change to it so that it would be undoing the chain rule? Everyone think about that. Everyone think about it. You should be able to see one small change to this that you would say, oh, yeah, then it would be undoing the chain rule. Okay, someone got it up in front. Yeah, Walker. Okay, yeah, that'd be another way. But if we wanted this whole thing, this product to be undoing the chain rule, somebody knew. You see what it should be? Nick? Yeah, so if there were a cube here, hopefully that's what most of you were thinking. If there were a cube there, then it'd be undoing the chain rule. Do you see that? Because the derivative of x cubed is something squared, right? X squared, and that's what we have as the pop-out, right? The pop-out from the chain rule. If this is something of the derivative of what's inside here, then we've got undoing the chain rule, and what would our first attempt be? What would our first attempt be? Absolute value of?
X cubed plus 1.
It'd be natural log, right? It'd be natural log because we'd be working on this, we'd be looking at this, and we'd do the antiderivative, keeping the inside the same. Okay, so all three of these web works that we've had in the last week have had lots of undoing the chain rule problems. Make sure that you can do that. Hopefully by now we're getting to the point where we don't need this whole process of first attempt, derivative, second attempt. The point is when you do enough of them, you can just look at it and write down the answer. And that saves you so much time over if you learned U substitution in the past. It's so much more efficient. So that's what I really encourage you to do. Okay, so if I just talked through that and you had no idea what I was talking about, then that's concerning, okay? Then you're not ready for the quiz on Friday. Okay. Any questions on that? Yeah. Okay, so part of the video was I gave the common forms, right? And if I can just do them off the top of my head, common forms like x to the n cosine or sine x, or it could be like kx, x to the n e to the kx, x to the n ln of x, and then there's other forms involving ln. So lots of times when there's a natural log involved, maybe it's undoing the product rule, but look for undoing the chain rule too with natural log. The arctan, arcsine, arccosine. So arctan, arcsine. So these are the most common forms that you look for undoing the product rule. These are the ones that, like the basic ones that show up the most. Okay. There's other kind of more obscure ones where undoing the product rule will work, and so then we're in the kind of the realm of trial and error. You just give it a shot and you work at it, see if you can make it work. If not, you look for another technique. But these are kind of the standard ones. And I might have missed something, but it's on one of the videos I did it. I think that's basically it. So I should just say, yeah, just natural. So just plain old natural log of x. That's undoing the product rule. And other forms involving natural log. Other questions? Okay, so now what if the degree of the numerator is not greater than or equal to the denominator? So let's look at the next one here. So if the degree of the numerator is less than the degree of the denominator, and the denominator can be written as the product of factors. So both of these conditions have to hold. If you can't factor out the denominator, you can't do partial fractions, this thing we're about to do. Okay? So these are the two conditions. You got to have the degree of the numerator has to be strictly less than the degree of the denominator, number one. And number two, the denominator has to be factorable. You have to get at least two factors apart in the denominator. Otherwise, we can't do this thing called partial fractions. Okay, all right, okay. So, degree of the numerator is less than degree of the denominator. What about the denominator? Can we factor it? Yes or no? Can we get that into... So we'd start by trying 2x and x. We need product of -1 summing up to -1. So I need 2x. I need product of -1, and then I need the sum of the middle terms to sum up to -1. So 2x plus 1. You're all thinking this, right? X minus 1. That gives us that middle term of minus x, right? So we got the 2x squared, we got the -1, and then 1x minus 2x is the minus, gives us minus x. Agree? Okay, so here's the deal with this. The way this works is, so we want to think about this as the result of adding two fractions. How do you add two fractions? You need what? A common denominator. So if we think about that factor denominator as the common denominator, we can think about that as the sum that came from the sum of two fractions, where one of the denominators was 2x plus 1, and the other was x minus 1. Because if we were to add fractions like that, what would the common denominator be? 2x plus 1 times x minus 1, right? So the question is, what numerators do we need so that when we add those together, we get this rate of change function that we started with? Okay, so the degree of the numerator that you're going to choose is unknown. So we don't know what these numerators are right now, but we need to know, we need to start off with the degree of it. The degree of it will always be 1 less than the degree of the denominator. Okay, so what are the degrees of my denominators here? First, right? So 1 less is 0th degree, or constants, just constants. So if you have a linear denominator, you're going to have a constant, an unknown constant for the numerator. So if we can figure out what a and b are, such that the sum of these two fractions is the rate of change function we were given, then we can do an antiderivative on each one separately. We just add them together, right? So just the whole point of the partial fractions is what are a and b. If we can figure out what a and b are, then we're done. We have a new form of the rate of change function that will be easy to write down the antiderivative of. Whereas this, none of our techniques work so far, right? It's not undoing the chain rule, it's not undoing the product rule, but it does fit this criteria for partial fractions. Okay, so what do we do? Now we're going to add. We're going to add these fractions. So when we add these fractions together, so I'm going to do it outside of the integral now. So just the rate of change function, we're going to rewrite. Could you add those together? Could you add a over 2x plus 1 plus b over x minus 1? How do we do it?
Multiply by something to get a common denominator.
Yeah, right. So again, so it's like we decompose it, and we put the unknowns in there, and now we're going to add it back together to figure out what a and b are. So we're going to add this. So we're going to just like take it apart, put it back together again. So we're going to have, what are we going to multiply the first fraction by to get ready to add? So hopefully you're thinking x minus 1 over x minus 1. And then b times 2x plus 1 over? Yeah. So and future examples, you don't have to, there's some steps we can skip here, but on the first one, I want to just kind of do it really out explicitly, okay? But in the future, we can kind of do half as many steps. All right, so then what do we get when we add together? So now we've got a common denominator, 2x plus 1, x minus 1, and that's familiar because that's exactly what we have in our original rate function. And then a numerator is? Everything added, right? So how are we going to find a and b? Well, what does all this have to equal? Right, so for this to work, we need the values of a and b such that that numerator equals 5x plus 1. So here we go. So we can just multiply out. So ax. So I'm just going to take the numerator now, because the denominator is done. So just the numerator would be ax minus a plus 2bx plus b equals 5x plus 1. If I lose you, please ask. Did I lose anybody? See what we're doing? Okay. So then we're just going to match up. So we're going to match up like terms, right? So we got our x values. I'll do blue triangles. We got an x term there. We got an x term there. And over here we got x term there. So we're going to gather those together. Since they all have x's, all we care about is the coefficient. So what do we know? A plus 2b should equal 5. Right? If ax plus 2bx equals 5x, then a plus 2b equals 5. And then we got our constants. Minus a plus b plus 1. Red circles. Minus a plus b equals 1. And what do we got? We got a system of equations. System of two equations of a and b. So any way that you can solve this, you're free to do so. I'm not going to require that you learn a certain way or do it a certain way. So there's elimination, substitution, matrix method. We're going to have these systems of equations. So any way that you want to do that is fair game. So this one looks like it's rigged for elimination. Do you see that if we could just add these equations and a's goes away? See that? If we add equations, a goes away. And so what about b's? How many b's do we have? 3b equals, so what? I just added equations. I added the a's, I added the b's, and the constants. Therefore, b equals 2. Come back here. If b is 2, then a is 1. Just use either equation to solve for a. Once you have one of them, you can easily solve for the other. And we got it. So we're pretty much done. We know that b and a are, so b, a equals 1. b equals 2. And now we got an easy integral. So that now we've got a variation on the form of the rate of change function that we started with. That's easy to do, right? So final step is we can write the original integral as 1 over 2x plus 1 plus 2 over x minus 1 let's see, tell me your name with the glass. Oh, Chelsea, here you go. Tell me what integral of 1 over 2x plus 1 is. Good. And also don't forget the absolute value. Okay, then what about 2 over x minus 1? Absolute value. Yeah, don't forget. Done. Okay, anybody have a question on this example? That's an easy one. We're going to do a harder one next. But it's all about just writing another, decomposing a single fraction into what's called partial fractions, right? So a bunch of fractions added together, that we can do the antiderivative through known techniques, right? Lots of natural logs will be involved because we'll have these factors to the -1, right? Lots of times we get these factors to the -1, so these end up being lots of natural logs in the answer. But other things do come up as well, okay? So it's not just all natural logs. Question?
I assume when we get like higher degree polynomials, we'll end up having like systems of equations with like three or
right. So actually, that's the next one we're going to do. So the next one we're going to do is going to have three variables, 3 equations. Ask before we do the harder one. Any questions? Okay, here we go. Last chance, gonna erase. Okay. Okay, first question we ask is it undoing the chain rule? Is it undoing the chain rule? No, not even close, right? First of all, we've got virtually we have three things multiplied together, right? We have x squared plus 1, x minus 3 to the minus 1, x minus 2 to the minus 2. So not looking good for undoing the chain rule, right? Undoing the product rule. I don't recommend it. I mean, you could go for it, but it just might get ugly, okay? So it might be fun. There's a chance it could work out if you happen to pick everything just right. But this is, we got a rational function. Is the degree of the numerator less than the degree of the denominator? What's the degree of the denominator? It's 3, right? It's because x and x squared. So if we were to multiply that whole thing out, we'd have an x cubed term. So degree of the denominator is 3. So, and then can the denominator be written as factors? It is already. So a big yes, right? Capital letters yes, right? Because that's what they're giving us. They're giving us a factor denominator. So they're just like saying partial fractions, right? Do partial fractions. This is begging you to do partial fractions. So here we go. We're going to rewrite it as. Now here's a kind of a strange thing. If we were to have added fractions together to get this, we have to take into account all possibilities without being redundant. So we need every kind of exclusive possibility that could have gone into adding together to get that without being redundant. So what are the possibilities? We could have had something with x minus 3, right? What else? We could have had something with x minus 2 squared. Now, is there anything else that we could have had that could have added into these fractions that to result in that common denominator? Just x minus 2. Now, if you want to know why that is, I'll make up an example using just values after class. I don't have time to do it, but I could come up with an example, something like 12. So something with 12ths. Something with 12ths could be the sum of some number of thirds, some number of fourths, and some number of halves. Okay? If you just try to get some number of 12ths with some number of thirds and some number of fourths, it's possible that you won't be able to do it. Okay? It's possible. And if you try to do it just with some number of thirds and some number of halves, it's also possible you can't do it. So if we're saying we don't know, and we want to make sure we include all possibilities for getting some number of 12ths, we need some number of fourths and some number of halves to do that, and some number of thirds. And that's the same exact analogous situation here. We got to take into account that there may have been something over just x minus 2 and something over just x minus 2 squared. So why not something over x minus 3 times x minus 2? Well, because that would be taken care of in the sum of these two. You see that? So these two added together, the first and the third, would already take care of that.
It's like the same reason you didn't write things over 6 with that little example.
Right, exactly. So
2 times 3.
right, we don't need some number of sixths to get some number of 12ths, right? Okay. So the question is now our numerators. Now what did I say? I said it's always going to be 1 degree less. But there's kind of a catch to it, okay? There's a catch to this. So for sure this is A. And I'll go with this as C. Now, I know that looks like a quadratic, but it's a linear term squared. It's a power of a linear term. Because of that, it's still considered a linear term. Okay? So it's only if it's like an irreducible quadratic that you would do a linear term up top. Remember I said it's one less. You're going to always pick an unknown expression that has one less degree in the top. But if you have any power of a linear term, you still consider that linear. So one less than linear is still constant. So we still think of x minus 2 squared as linear. So we just use a constant up top. So what we would need is a quadratic that can't factor into a linear squared or linear cubed. And then we would put a linear term up there. So if we had some unfactorable quadratic, that's what you're going to ask, right? Some unfactorable quadratic, then we would have something like bx plus c, or in this case, bx plus d, a general form of a linear term. Okay, does it make sense? Okay, so then we're off to the races here. So we know that we're going to add these three together. So what do we need to multiply top and bottom by? So we're going to go right to the numerator equation, okay? What do we need to multiply top and bottom by on this first one to get the common denominator? You should see x minus 2 squared, top and bottom. So that's going to give us a times x minus 2 squared. What do I need to multiply top and bottom by on this one to get the common denominator? Just x minus 3. And then what about this one? So I've got one x minus 2, and I'm trying to get what? X minus 3 times x minus 2 squared. So what am I going to multiply top and bottom by on this? We're going to need one more x minus 2, and also an x minus 3. Do you see what I did? So I'm thinking about what the numerator would end up being when I got a common denominator and added them together, right? Common denominator would be, this is our common denominator. So this first one already has one x minus 3, so I need both the x minus 2's. This has both the x minus 2, so I just need one x minus 3. This has one x minus 2, so I'm going to need one more x minus 2, and I'm going to need the x minus 3. So that's going to be the numerator, and we know that numerator is going to equal? It needs to equal x squared plus 1. We need to know what are the values a, b, and c that'll make that thing equal to x squared plus 1. Okay, if I lost you, please ask. No? Everyone good? All right, so here we go. I'm going to write it out fast. Ax squared minus 4xa plus 4. So I'm expanding to x minus 2 squared plus bx minus 3b plus cx squared. What's our middle term? Is it minus 5x? So if I make a mistake, please tell me, because this can dig a bad hole that'll waste a lot of time. Plus 6c. How did I do? I think I did okay. Equals? Okay, x squared terms. So we're going to gather up terms. We got the x squared here. Blue triangles. And there. And there. There's my x squares. I got my x's. What's my x over here? 0x. And then constants. Did I make a mistake? Okay, yes it is. Thank you. Thank you, good catch. You can look right now. So our equations are A plus C equals what? 1, right? So ax squared plus cx squared equals 1x squared. So a plus c equals 1. That's my blue triangle equation. Then the reds are the linears, right? So minus 4a plus b minus 5c equals 0, right? And then my constants are 4a minus 3b plus 6c equals 1. Also 1. So now we got 3 variables, 3 equations. Again, any technique, substitution, elimination, matrix method, something else. Do anything you want. So one thing we could do is we could eliminate b from these last two, and we'd have a and c, and then we'd have 2 equations of a and c. I'd have a plus c is 1, and a new equation of a and c. And we've got it down to 2 variables, 2 equations. So let's do that. So I want to take this one here, and I want to multiply it by 3. And then I'm going to be able to get rid of b on these 2. So how many a's will I have? I'll have negative 12a plus 4a. Is that negative 8a? And then we got 3b minus 3b is 0. And we have minus 15c and 6c. What's that? Is that minus 9c? And then 3 times 0 plus 1. Check my work. Did you catch what I did? I multiplied the red equation by 3 to eliminate b. And so then I got, check it again, negative 12a and positive 4a, negative 8a, negative 15c, and 6c is negative 9c. I think that's right. So now we've got 2 equations, 2 variables, right? So I can combine that one and that one. And now I'll use substitution. So what is a, to just try something different here, and it will, substitution lends itself well here. A equals what? A equals 1 minus c, right? If I solve this top one for a, so I can plug in 1 minus c for this. So we can say minus 8 times 1 minus c minus 9c equals 1. And then we're going to have 8c, so minus negative c minus 8 plus 8 equals, I think c is negative 9. Anyone else get that? Someone did? And if c is negative 9, then a has to be, from this one, 10. Then we could use either one of these to figure out what b is. Use the bottom one. So 40 minus 3b plus negative 54 equals 1. Negative 5. So you got that too? So what does it mean? It means that this original rate function is equal to, what, 10 over x minus 3 plus negative 5 over x minus 2 squared. We got one more example after this. Plus Negative 9 over x minus 2. Questions on solving that system of equations? Did I lose anybody? Don't hesitate to ask. So then this right here is equal to super small 10 over x minus 3 plus negative 5 over x minus 2 squared plus negative 9 over x minus 2. So we'll just talk through it. I'm not going to write down that. So now we're ready to do antiderivative. This is all doable now. Antiderivative of 10 over x minus 3. 10 ln absolute value x minus 3. What about this? This natural log? Minus 5 over x minus 2 squared. Is that natural log? Nope. What will it be? To the what power? To the negative first, right? This is something to the negative 2. So it'll be to the negative first. X minus 2 to the negative first. You'll have a 5. You got to work out the signs. Okay? Get your plus or minus correct. Make sure the plus or minus is correct. This is another natural log. So easy, 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 easy. Okay? Plus c. Questions on this example? Okay, so let's look at one where we have an actual. I got one more example that we talk about.
I have to tell them it's the point before you let them go.
Oh, well, we can. What do you think?
I was thinking optional for either.
Yeah, sure.
Okay.
Yeah.
Everyone, today's recitation is optional for anyone from either Wednesday or the one's help with project. Okay?
Okay, so one more example. It's shorter example, but it brings into this this thing with the square. Last chance. Can I erase? Here we go. So this one, degree of the numerator less than the denominator, and we can factor the denominator into what? How's this factor? X cubed plus 4x. Factors as x and x squared plus 4. So we're good for partial fractions. It meets both requirements. The degree of the numerator is less. We should have asked, is it undoing the chain rule? Nope, because we need to have all kinds of powers of x on the top for that to work. So it's not undoing the chain rule. Okay, so it works for partial fractions because the degree of the numerator is less, and you can factor the denominator. Okay. So here we go. So we're going to have a over x. Now, this is a true quadratic because it can't be, it's not a linear squared, right? It's not a linear term squared. You can't factor that. It's stuck as a quadratic. So that's when we do the one less the bx plus c is one less a generic linear term, right? But now everything else is the same. It's going to be a times, the numerator will be a times x squared plus 4. And then maybe bx plus c times. What do we need top and bottom here? An x, and that's going to equal. So there's our numerator equation. It's a numerator equation. And we'll have ax squared plus 4a plus bx squared plus cx equals 10. The triangles. red circles. So we have a cx term, right? Cx. We have 0x. Make sure we just have a constant 10. So that means 0x squared and 0x. And then so we're going to have a plus b equals 0. C equals
0.
like that, right? That's helpful. And then 4a equals 10. Therefore, this is really easy, right? A is
2.5.
5 halves. B is negative 5 halves. C is 0. So you put them in. So you're going to have 5 halves over x plus negative 5 halves x over x squared plus 4. Let's just talk about that. Antiderivative, so negative 5 halves over x. Sorry, positive. Plus negative 5 halves x over x squared plus 4. First one's easy. What's this? So negative 5 halves x over quantity x squared plus 4. How do we do that?
That's like
Undoing chain rule, right? Undoing chain rule because we got x squared plus 4. And we have essentially have its derivative outside of there, right? There's the x to the first. So this is, that one would be undoing chain. Okay, so you'll have web work on this due Friday, but then the quiz will not include this. It'll include the other techniques so far on Friday, okay? And then, yeah, optional recitation today.